Sewage Analysis and Treatment, Part 1. Environmental Engineering, Module 4 and Module 5. This is for the Diploma, Unit 3.5 and 3.6, and for B.Tech, CEPC 505. So far in this subject, you have learned how to move sewage, how much of it a town produces, what shape of sewer carries it, how fast that sewer must run. Today, the sewage arrives at the plant and we ask a different question: what is actually in it and how do we take that out? Here is the one idea that carries this whole topic. A treatment plant removes things in order of size. The big first, the dissolved last. Screens take out what you could pick up with your hand. Grit chambers take out what would sink in a bucket. Sedimentation tanks take out what sinks slowly. And only then does the plant go after what is dissolved. And for that, it stops using gravity and starts using living organisms. Every unit you are about to see is one more step down that ladder of size. Treatment is described in 4 stages, and naming them correctly is worth marks before you have drawn a single tank. Preliminary treatment removes floating matter, rags, and grit. Primary treatment removes the settlable suspended solids. Secondary treatment removes the dissolved and colloidal organic matter. Tertiary treatment removes whatever is left, mostly pathogens and nutrients. Now notice 2 things, because examiners ask both directly. First, preliminary and primary are both purely physical. The difference between them is speed. A grit chamber is designed so that only grit settles in under a minute. A primary tank is designed so that everything settleable settles over several hours. Second, secondary treatment is the only biological stage in the entire plant. It is the only place where something living does the work. Say the stage before you name the unit, and your answer organizes itself. This is the drawing to memorize. Almost every long question in this topic begins. Describe the treatment of sewage with a neat flow diagram. Read it as 2 lines running side by side. Down the left is the water line. Raw sewage arrives from the sewer. It passes the screens, then the grit chamber. That is preliminary treatment complete. It flows into the primary sedimentation tank where the settleable solids drop out by gravity. It goes on to biological treatment, then to a secondary sedimentation tank, then to disinfection, and it leaves as treated effluent. Every box on that line makes the water cleaner. Down the right is the sludge line, thickener, digester, drying beds. Every box on that line makes the removed solid smaller, safer, and drier. And these 2 dashed arrows join them. The primary tank and the secondary tank both hand their settled solids across. Remember this, a treatment plant does not make dirt disappear, it concentrates it and then it deals with it separately. Before you can design anything, you must measure what you are treating. The characteristics of sewage fall into 3 families: physical, chemical, and biological, and every one of them exists to answer one of 3 questions. How strong is this sewage? That is answered by the organic matter. How much solid is in it? That is answered by the solids test. And how dangerous is it? That is answered by the bacterial count. Keep those 3 questions in your head, and the long list of parameters stops feeling like a list. Physical first color. Fresh sewage is grey. As it goes stale, as it turns septic, it goes black because the sulfides forming inside it are dark. An experienced operator can judge the age of the incoming flow by color alone. Odor. Fresh sewage is musty and not strongly offensive. Septic sewage smells of hydrogen sulfide, the rotten egg smell. Temperature is slightly above the local water supply because of warm water from kitchens and bathrooms, and that matters because biological activity speeds up as temperature rises. Turbidity is a quick measure of the suspended matter, and then solids, which is the one that carries marks. Total solids split 2 ways at once. By filtering, total solids equals suspended solids plus dissolved solids. By burning, total solids equal volatile solids plus fixed solids. Volatile means organic. Fixed means mineral ash. Learn both splits. One trap before we move on. Settleable solids are the part of the suspended solids that will settle under gravity in a stated time, and they are measured in an Imhoff cone. They are reported in milliliters per liter a volume, not in milligrams per liter. Every other solids figure is a mass. Get that unit wrong and you lose the mark. Now the chemical characteristics. The pH of fresh domestic sewage is close to neutral and a sharp swing tells you an industrial discharge has entered the sewer. Nitrogen appears in a chain and the stage it has reached tells you how fresh the sewage is. Organic nitrogen, then ammonia, then nitrite, then nitrate. Plenty of ammonia means fresh. Plenty of nitrate means already well oxidized. Phosphorus and nitrogen together are nutrients, and discharging them makes the receiving water bloom with algae. Sulfates matter for a different reason. Under anaerobic conditions, bacteria reduce them to hydrogen sulfide, which oxidizes on the crown of the sewer into sulfuric acid and eats the concrete. That is crown corrosion. Now, the single most asked term in this subject, biochemical oxygen demand. BOD is the quantity of oxygen required by microorganisms to oxidize the biodegradable organic matter in a sample, under stated conditions of time and temperature. Three phrases in that sentence are doing work, required by microorganisms, so it is a biological measurement. Biodegradable, so anything the microbes cannot eat, is invisible to the test. And under stated conditions, because the number means nothing without them. The international standard is 5 days at 20 degrees Celsius. Indian effluent standards are written for 3 days at 27 degrees Celsius. Because our climate is warmer, how is it measured? Sewage holds far more organic matter than the oxygen in one bottle of water could ever satisfy. So we dilute the sample with well aerated water. We measure the dissolved oxygen at the start, seal the bottle, incubate it, and measure the dissolved oxygen again at the end. The oxygen that disappeared was eaten, so BOD equals the drop in dissolved oxygen multiplied by the dilution factor. Let us do one. 5 milliliters of sewage is diluted to 300 milliliters. The dissolved oxygen falls from 8.0 to 3.2 milligrams per liter over the incubation. Step 1. The dilution factor is 300 divided by 5, which is 60. Step 2. The oxygen consumed in the bottle is 8.0 minus 3.2, which is 4.8 milligrams per liter. Step 3. Scale back up. 4.8 times 60 is 288 milligrams per liter. Notice the dilution factor multiplies. It does not divide. Now the partner test. Chemical oxygen demand, COD, oxidizes the organic matter chemically with a strong oxidizing agent and no microbes are involved. So nothing is spared for being indigestible. BOD takes 5 days, COD takes about 3 hours. BOD counts only what is edible. COD counts everything, which means for the same sample, COD is always greater than BOD always. If a question hands you a BOD larger than the COD, the data is wrong and saying so earns you the mark. The biological characteristics, bacteria are the largest group, and the reason sewage is a health hazard. Viruses including polio and hepatitis are small and tough and survive treatment that kills bacteria. Protozoa and helminths, the cysts and the worm eggs, are relatively heavy and largely settle out in the tanks. Algae matter later in the oxidation pond. Fungi grow in the film on a trickling filter. Now here is the idea that questions are built on. We do not test sewage for every pathogen. That would be slow, expensive, and unreliable. Instead, we count the coliform group, the bacteria that live in the intestines of warm-blooded animals, of which E. coli is the most familiar. Why coliforms? Because they are always present when fecal contamination is present. They are present in far larger numbers than the pathogens. They are cheap and easy to detect, and they survive in water at least as long as the pathogens do. So a low coliform count is good evidence that the pathogens have gone too. The coliform is an indicator organism, not the danger itself, and the result is reported as the most probable number, MPN per 100 milliliters. Treated effluent is never simply clean. It must meet the standard for the place it is going, and there are 4 routes: discharge into inland surface water. A river or a lake carries the strictest standard because that water is used downstream for supply, for bathing, and for fisheries, and a small river has very little capacity to dilute. Discharge into public sewers carries the most relaxed standard because that flow is going to a treatment plant anyway. The limit exists only to protect the sewer and avoid overloading the works. Discharge onto land for irrigation and discharge to marine coastal areas sit in between. These general standards are laid down in Schedule 6 of the Environment Protection Rules, 1986. And note one Indian peculiarity worth quoting. Our standard specifies BOD at 3 days and 27 degrees Celsius, not the 5 days at 20 degrees used internationally. Preliminary treatment now, and the first unit is the screen. A screen is a set of parallel bars set across the channel and inclined at about 45 to 60 degrees to the horizontal. Understand this clearly. Preliminary treatment removes nothing that matters to the quality of the effluent. Its entire purpose is protection. A rag in a pump impeller stops a plant. Why is the screen inclined? 3 reasons, and a good answer gives all 3. It gives a larger screening area than a vertical screen in the same channel widths, so the velocity through the bars stays low. It lets the screenings be raked upwards and out instead of being lifted through water. And it reduces the head loss and the tendency to clog. Screens are classified by clear spacing as coarse, medium, and fine, and separately as hand cleaned or mechanically cleaned. And one rule that is absolute: screenings are never returned to the flow. They are buried, incinerated, or properly disposed of. The second unit is the grit chamber. Grit is the inorganic, heavy material that finds its way into a sewer, sand, silt, gravel, ash, eggshells. Left in, it wears out pumps, it abrades scrapers, and it fills up the digester with material that has no business being there. A grit chamber is simply a widened channel where the flow slows enough for grit to settle, and no more than enough. Now, this is the whole answer to any question on grit chambers. The velocity is the design. It is held at about 0.3 meters per second. Go faster and the grit stays in suspension and passes straight through. So the chamber has achieved nothing. Go slower and the organic matter settles along with the grit. And that is actually worse than doing nothing, because the organics are wanted downstream where they can be treated. And here they will simply rot in the grit heap. Detention time is only 30 to 60 seconds. That is all a sand grain needs. Primary treatment. This is plain sedimentation. Hold the sewage still enough, long enough, and everything heavier than water that is going to settle, settles. No chemicals, nothing alive. Gravity given time. Every sedimentation tank, whatever its shape, is described by the same 4 zones, and naming all 4 is usually half the marks of the sketch. The inlet zone, where the incoming flow is spread across the tank and its velocity is killed by a baffle. Leave the baffle out and the incoming jet runs straight to the outlet. Most of the tank becomes dead space and settling fails. That fault has a name: short-circuiting. Use the word. The settling zone is the quiet body of the tank where particles actually fall. The outlet zone, where clarified water is drawn off gently over a weir. And the sludge zone, the floor, where a slow scraper pushes the settled solids to a hopper. Tanks are built rectangular or circular. In a circular tank, the sewage enters at the center through a feed well, flows outward, and spills over a weir that runs all the way round the rim. Primary treatment takes out most of the settleable solids, and with them roughly a third of the BOD. What it cannot touch is what is dissolved. Gravity has no grip on that. And that is exactly why secondary treatment exists. Let us close part 1. A treatment plant removes things in order of size. 4 stages, preliminary and primary, are physical. Secondary is biological. Tertiary is the polish. The characteristics come in 3 families: physical, chemical, and biological, and they answer 3 questions: how strong, how much solid, how dangerous. BOD equals the drop in dissolved oxygen times the dilution factor, and COD is always the larger of the two. Coliforms are indicator organisms counted as most probable number per 100 milliliters. Screens protect the plant. The grit chamber is designed by its velocity 0.3 meters per second, and the settling tank has 4 zones: inlet, settling outlet, and sludge. What is still open is the biggest half. How do we remove the organic matter that is dissolved? That is part 2. where we meet the activated sludge process, the trickling filter, and the sludge line that deals with everything we have taken out. Study notes and the practice paper for this topic are on our Telegram channel. Free as always. I will see you in part 2.